Hello and welcome to another topic of notes in science. Today you can see our topic is called solar science. If you'd like to please set up your focus note page, the essential questions we are focusing on today are: what is the difference between fission and fusion? And what is the lifespan of our sun? So we're going to learn a lot more specific of the science and kind of chemistry that's going on in the sun as the center part of our solar system. If you are taking this on the date they were assigned, it is 11:05. Otherwise, fill in whatever date you are taking these notes. And remember, it's only the things that are not in white that I expect you to write down. All the other things are things that I just want to talk about and have you hear, but not necessarily things that you need to write down. And that's going to be really important today because there's a lot of cool stuff I want to talk about, but not necessarily things you have to write down. I want you to mostly be able to kind of listen and enjoy the story and just write down some of the most important things. So let's get into it. Solar science. The first thing I want to talk about is reactions in general. In the chemistry world, there are something called, well, in the science world, there are something called chemical reactions, and that's anytime you have particles that either separate to make something new, combine to make something new, or just kind of rearrange themselves and change their bonds in order to make something new. But what we are focusing on today are nuclear reactions. And in a nuclear reaction, it's the nuclei, which is the plural of nucleus. So you have one or two or more nuclei that split or combine, and this involves energy or radiation. So we're going to actually talk about some energy stuff like we talked about in our very first unit. We just kind of mentioned nuclear energy. We're going to get a little bit more of that detail today. Since we know more about science and energy and particles, we can talk about that a little bit more. So the next thing we want to talk about is generally the nuclear stability. And it turns out that it's not very stable. The nucleus is generally pretty unstable. And we think of the nucleus, remember, as protons and neutrons crammed together in the middle of an atom. Bigger nuclei are generally more unstable because what's happening here is that those positive and positive protons want to stay away from each other. And yeah, there's some gravity between the neutrons and the protons, neutrons and neutrons, neutrons and protons. There's some attraction happening there, but it isn't very strong. The protons are trying to get away from each other. So they're literally trying to push apart the nucleus. And the nuclear force of the neutrons is very weak, and it actually stops when the neutrons are too close together. It's like they just can't attract very much anymore. And since the nucleus is so dense, those particles just don't want to stay near each other. So that makes the nucleus pretty unstable. And then the bigger elements are even more and more unstable. So then what can happen is that nucleus or can start to split apart, nuclear decay. So when an unstable nucleus falls apart, that's called nuclear decay. There's three different types of decay that I just want you to be aware of: alpha, beta, and gamma. And these are just the Greek symbols for these three terms: alpha, beta, and gamma. When you have alpha and beta decay, you actually produce new elements. So when that nucleus falls apart, however many protons stay in one part of the nucleus, if you add up those protons, that would define what element you have. Eventually, as the unstable nucleus falls apart, it will decay to a stable element. It won't be radioactive anymore. There's no reason for it to keep splitting apart. And then you just have that different atom than you started with. So that process of nuclear decay, we actually can use that in different ways. This is also useful, this nuclear decay is also useful for getting rid of radioactive materials, like from a power plant or from somewhere. If you let it sit long enough, many radioactive materials will just split apart to create something that is stable and then not radioactive anymore. And so that's a positive thing. But we can use this nuclear decay to produce new particles and to produce some energy. And that's a big deal. The other thing related to decaying is carbon dating, which maybe you've heard about. All living cells contain carbon. So whether it is a plant or a person or an animal or whatever, inside those cells, you have both carbon 14 and carbon 12. Remember, these are different isotopes of carbon. And when something starts to decay, so if you have plant material that's decaying in the woods, or a raccoon on the side of the road, or a person, if something is decaying, the carbon 14 doesn't form anymore. And so it starts to break down. So then what can happen is scientists can study how much carbon 12 is there and how much carbon 14 is in that sample. And they can use what's called the half life of carbon 14 to determine how long something has been decaying. And it turns out that it takes about 5,730 years for the carbon 14 to get to its half life, so that you'll have half of the atoms left over. So if you've ever been to a museum and you've seen something from ancient history that we predict how old it is, that could be because of carbon dating. So, like plant materials or fabrics, like Dead Sea Scrolls or the Shroud of Turin, which was like a burial shroud that was covering something, those, because they're made of plant materials, we can see what is left and we can use carbon dating to figure out how old they are. So that's just kind of a little side note. Like you said, if you've ever been to a museum and they've said that something was, thousands of years old and you wondered how they figured that out, it does have to do with isotopes and particles and nuclear decay. So then the last piece of this kind of introduction I want to talk about is, okay, well, how do we know something is decaying or if it's actually producing like a chemical reaction? So what's the difference between nuclear decay and a chemical reaction? In a chemical reaction, it is the electron that is being changed, exchanged, bonded with other things, and that's what causes the change. In a nuclear decay reaction, it's the neutron that is causing the change. So because the neutron is kind of falling apart from that nucleus, then you get different amounts of protons in your nucleus. So then you get different identities, different atoms. So that's the big difference between them. Okay, go ahead and do your first brain break. So just of the things we've talked about so far, write a question that kind of goes right from the notes. So look at your notes so far, gives you a chance to kind of process them and see what makes sense. A list, a definition of something. Those would all be good kinds of level 1 questions. Go ahead and write your level 1 question. All right. So there are 2 types of nuclear reactions, because eventually, remember, we're trying to explain what's going on in space, in our sun, in our universe, right? So that's what we're getting to. So 2 types of nuclear reactions, fission and fusion. Now, in general, both of them mean something is happening to your nucleus. That's why they're called nuclear reactions. If you look at these 2 pictures, see if you can figure out what is happening to the nucleus in fission, what is happening to the nucleus in fusion. Can you figure it out? See if you can make a prediction, do some thinking. All right, well, let's define the 2 and then we'll see if you were right. Okay, let's start with fission. Fission is when the nucleus of an atom splits into smaller parts through reaction or decay. So you can force a chemical reaction to happen, or you can just let it decay on its own. You can usually make this happen by taking a neutron, that's what this is showing, and you fire it at the nucleus of an atom, and that causes it to split apart. And then, maybe some neutrons kind of also fall off and gonna go into space as well. But the idea of using this, so fission splitting up into different atoms, that also is going to release some energy. That's what this squiggly line is trying to show. So then we can use that energy to make something happen. So here's some fission equations just to kind of see. So if we fire a neutron at uranium-235, that's a common fuel used for nuclear reactions. Quick little side note, what does that 235 mean again when we put it with the name? Yep, that's its mass number telling you what isotope of uranium we're using. And so if I take uranium-235 and I blast it with a neutron, what happens is these smash together and then this nucleus splits apart. And it might split into rubidium, which has a mass number of 90, and cesium, which has a mass number of 144, and then 2 extra neutrons. But take a look at this. If you add up these 3 numbers, 90 plus 144 plus 2 extra neutrons, it equals 236. Because this is 235 plus 1 more neutron, this is also 236. So the idea is that the amount of particles you started with was 236, and you still have 236 particles on the other side. That's an important thing in science, that you can't suddenly lose particles or get more particles from nowhere. They have to be accounted for. Here's another one. Again, neutron blasted at 235. It could create krypton with a mass number of 93, barium with a mass number of 40, and then 3 neutrons. Okay, so let's check our math again. 93 plus 140 plus 3 equals, again, 236. Well, that makes sense because, again, I have 236 on this side. Let's also check our protons. If you look on the periodic table, uranium has 92 protons. Krypton has 36, so remember that. Plus barium has 56. So if I take 36 plus 56, 36 plus 56, that equals 92. That makes sense because uranium has 92 protons. And then if we added up all the neutrons, that's where we got the total 236 on this side, 236 on this side. So sometimes then we can make predictions about reactions. So if we did what we just figured out over here, so I have uranium on this side, and that's 92 protons. And then it says it produces bromine. If I look on the periodic table, bromine has 35 protons. So if I take 92 protons minus 35 protons, I should have an element here with 57 protons. I look at the periodic table. Oh, where is number 57? Number 57 is La, lanthanum. So the element that appear here should be La, lanthanum. And then let's figure out what the mass number should be. It should add up to 236. So I've got 236 total minus, I already have an 87 right here. And then minus, I have 3 neutrons left over. So that gives me a mass number of 146. And then we figured out that the element was lanthanum because of the protons. So using some of the stuff we know about chemistry and protons and the periodic table, we can make some prediction about some fission things that are going to happen. All right. Let's talk a little bit more about how this is related to energy. There's energy in the nucleus, so there's energy stored in the nucleus, and you can cause those, if you can cause that nucleus to break apart, those particles will move, and that can produce kinetic energy. All right. So we can use the energy in the nucleus for negative things like the atomic bomb, destruction, but we can also use it for good things like nuclear power. And that's what I want to talk about quick next. So if we use the energy stored in the nucleus, we can actually generate electricity. And I want to show you how that happens. It's actually not so complicated that you can't follow along. So let's talk a little bit about how we use fission in a nuclear power plant. So here we go. Here's your uranium pellet, a piece of uranium that gets put in a metal tube kind of. And then that gets, a whole bunch of those tubes create a nuclear reactor core. And then we fire particles at the uranium, and the uranium split. And that causes energy because the particles are moving, and it also produces a lot of friction and heat because the particles are moving. So that whole core gets really, really hot. But that core is sitting in water. And so as the water heats up, steam, gas particles are created, and then that gas starts moving and filling up the space. And it goes into these pipes, and the steam keeps moving because it has lots of energy. So moving, the steam goes through those pipes, and eventually the steam hits the turbine. The turbine then moves, and then that is what creates our energy, and then that what creates our electricity. Well, that steam can be cooled down and condensed back to water, and then that water can return. Just showing the water right now. The water goes back to the beginning, and the whole process can repeat. So the cool thing about nuclear power is that even though you have to start with uranium, which can be a little bit scary for some people, it's very clean, and you can keep using that water over and over again. So that's kind of the positive parts of nuclear power. There happen to be 2 nuclear power plants in Minnesota. If you were not aware of that, I just want you to know. So we're kind of in this area. Here's Roseville. A little bit north and west is the Monticello nuclear power plant. And then there's also one in the lower, so like southeast part of the state, there is Prairie Island. This is actually, look, I live in Albertville, so I actually live really close to this power plant. Just a little side note from Miss Killinan. All right, anyway, so that's the chemistry and the science behind nuclear power plants with fission. And then I just want to connect this to the energy pie charts that we learned how to do earlier this year. So start with a pie and put En in the center. There's your energy nuclear. And then the En transfers to energy kinetic because of the moving particles. But remember, anytime there's moving particles, there's also energy thermal. The particles are colliding, they're moving, that causes energy thermal. So part of your pie is also energy thermal. And then the energy thermal heats the water, turns the water to steam. The steam powers the turbine, and then you get useful energy, you get electricity. So En transfers to Ek and Et, and you get a lot of Ek out of it, which is really good because that moves the turbine, which is the useful piece of the energy. So just explaining a little bit more in terms of energy pie charts, what's happening with fission, where we split the atom and the release of energy creates the energy like we just talked about right here. All right. Now, the side note about why people get nervous about nuclear power plants is that nuclear fission can cause a chain reaction. So the idea is that when you blast those particles of uranium with something, those particles start breaking apart, and then those particles break apart, and then those particles break apart, and that could keep happening over and over again, a chain reaction. And if it just keeps going, it can be difficult to control. And the whole time it keeps going, it's producing more and more and more energy. But the good news is that nuclear power plants have what are called neutron absorber pads that absorb the extra neutrons so that they can't just keep hitting other atoms and creating more and more fission. So that's a protection in place. The atomic bomb takes advantage of the fact that you can start a chain reaction and just let it go. So you take that, there's uranium in the bomb capsule, and you blast it with some sort of particles, you ignite it and let it release, and then that's why it creates so much damage. It's because the chain reaction is not caused to stop, so it just keeps going and going as much as it can, and it releases lots and lots of energy. And then the effects of nuclear energy, remember our definition of energy, it's the capability of producing change. So when the nuclear reaction happens, you have particles that are moving really fast, and that can occur naturally or it can happen in a power plant. But when these particles are moving so fast, that's a lot of energy. And if those particles hit living organisms like plants or animals, they can damage cells. So there is some truth to the idea of nuclear radiation, of course, can cause damage to cells. Damaged cells can lead to cancer, and about 1% of all cancer cases are caused by radiation. So obviously it's a real concern, but it is not the thing we're most concerned of when we talk about cancer and damaging cells. You might have heard in 2011, there was a nuclear power plant explosion in Japan, in Fukushima, and it was because there was an earthquake and tsunami right near the power plant, and then that caused one of the nuclear cores to break apart, and then that created a chain reaction that just happened so quickly it couldn't be contained. So not a normal thing that happens at all, but that was where that came from. And you might have heard of Chernobyl or some other nuclear power disasters, but they are not very common, but they did cause a lot of damage to living things because of all of the energy being released and not being controlled. All right, so that gives you kind of a background of fission. So going to a level 2 question so far. We didn't really talk about it too much yet, but you could say compare fission and fusion. We just barely talked about it. You could say sketch a picture of a fission reaction, like what it would look like, or sketch a diagram of a nuclear power plant. That'd be kind of a cool level 2 kind of question. Okay, so all of this has been kind of background side story related to other things we've talked about. We've talked about neutrons and atoms and energy and pie charts and those kinds of things. But now let's get into what's going on in space, and that is fusion. When two or more nuclei collide, and when they collide, they don't split apart, they join and they form a new type of atom. This is what's happening in our sun. So finally, we're making the connection between all that other science, chemistry stuff and our solar system. So fusion is what is happening in the sun. All right, so fusion examples. So here are some equations related to fusion. So if I have hydrogen, which has a mass number of 2 and an atomic number of 1, and another hydrogen that has a mass number of 1 and atomic number of 1, you've got 1 proton and 2 protons. So now you can produce helium plus a bunch of energy. If you did that with hydrogen with a 1 proton and helium with the 2 protons, 2 plus 1 is 3 protons, that would now be lithium. And then that would produce a bunch of energy. And then notice also that the mass number is equal. So 1 plus 2 is 3 mass number, 4 plus 3 is 7 mass number. And the element changes because of the protons that are adding together in the nucleus, colliding to make something new. It's pretty hard to recreate this on Earth because when it happens in a star, think about how much EPG there is in the star. EPG is like how much space it could move or fall. So if you're way out in space, you have a lot of room that you could move or fall. We just can't produce that much EPG here in lab. So when we try to heat up atoms to make them collide and fuse together, fusion, we end up using way more energy than we can produce. And that's just kind of like a waste of energy, right? So we have not been able to make fusion happen here on Earth, but it's something that we can study and we can theorize based on what stuff is happening in space. Here's just a visual of carbon's fusion. So you've got the carbon atom, which has 1, 2, 3, 4, 5, 6 protons. If that combines with a hydrogen atom, so fusion between carbon and hydrogen, you'll get nitrogen because nitrogen has 1, 2, 3, 4, 5, 6, 7 protons. And then if that then loses a proton, then you get carbon and hydrogen again. That can make nitrogen. If nitrogen and hydrogen combine, you get oxygen. And then that can just kind of keep happening. So fusion is when the nuclei combine. And when they come together, then that's where you create new atoms. And it turns out that if you look at all the elements on the periodic table, fusion basically stops, and then you would switch over to fission if you get to iron. So atoms that are smaller than iron, so 26 protons or less, those atoms are going to take part in fusion. And eventually those atoms will fuse to form iron, and then the iron is not radioactive, it just kind of stays there, doesn't produce any more energy. But atoms that are larger than iron are more likely to take place in fission. So bigger atoms are more likely to decay and fall apart, that's fission. Smaller atoms are more likely to collide to create new atoms up until iron. So that's just another little connection between some of those atoms on the periodic table. Okay, let's put all of this together and let's think about what's happening in stars. So I've got one more video I want to show you, and this video helps you understand more about the life cycle of stars. Let's go ahead and check this out.
Well, way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself, and towards the center of that cloud, it gets denser and denser, it gets hotter and hotter. And eventually, the particles that the gas and the dust are made of are brought so close together that they start to stick together. They start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out. And at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the sun, this will be the beginning of the end.
What happens is that the outer layers of the star get farther and farther from the middle. The force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object. It's dead. There's no nuclear fusion going on it anymore. It's incredibly hot, but then over millions of years, it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang, the outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun, but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star billions of years ago before the Sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our Sun, the planet Earth, and indeed ourselves were made. And actually, I think that ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
Okay, so now you know a little bit more about how stars work in space. And so what I have for you is, let's kind of summarize what we just went through. Okay, so stars start because there is space dust out there that pulls more and more and more pieces together. Eventually it accumulates more and more mass. When those pieces get close enough, fusion can begin. The atoms can actually collide and combine, and you can create new elements. All stars begin by fusing hydrogen into helium. So you take one hydrogen and another hydrogen. When they collide, you get two protons. That's helium. And that just happens over and over again. All right. So then when that happens, gravity tries to keep the star together, but the energy being released pushes the star apart. So you have that balance of kind of the star wanting to come inside itself and to spread way out. So kind of going back and forth, back and forth. Once the hydrogen runs out, so there's no more hydrogen and hydrogen left to make helium, you have helium that can make other things and so on, the star's life cycle begins to change. And then eventually there's more and more gravity at the center. And then on the outside, everything has spread apart so far that it just kind of drifts out into space. And the difference between that lots of gravity in the middle and the super spread out pieces on the outside that just spread out into space, that's kind of when he popped the balloon, like the explosion piece of it. So when we think about the science of stars, the size of the star determines what life cycle it will have. So the life cycle of our sun would follow this path of the small star. So way back when, in that Big Bang, there was some particles of space dust that came together to make our sun. And then our sun at some point will continue to fuse hydrogen into helium, and that will continue. And eventually our star will expand and it will sort of collect or absorb those inner planets. And then it's a red giant. And then as that creates more mass and also energy, and the red giant spreads out, you'll produce this thing called that planetary nebula. So the outside is just these beautiful pieces of energy that are spreading out. And then the inside is a really, really, really dense and heavy, all of the waste weight and the gravity is smashing inside itself. And when the outside spreads out enough and that inside the gravity has just sort of collapsed everything into one little spot, that's a white dwarf. If you have a larger star, then it goes through that same process, but it can create something called a red supergiant. And then eventually when that explodes, it creates a supernova. And then depending on the size of that supernova, it can create sort of a neutron star, which is kind of the idea of a white dwarf. Or if its supernova is big enough, as it collapses into the center. So when the outside spreads out far enough, but the inside is so dense and so much weight, that's when they say that you can create that black hole. And that gravity is so strong that not even light can escape from that black hole. So these are different life cycles depending on the size of the star that you start. So we would say that the life cycle of our sun fits this pattern. So from a small star to a red giant eventually, not in the next couple years, but at some point, and then into a planetary nebula, into eventually a white dwarf. And that brings us to the end of our solar science and the science happening out in the universe. So go ahead and do a level 3 type of question, something that really makes you think and be creative. Like imagine what will happen when our sun turns into a supergiant or something like that. All right. Okay. So finish up your level 3 question, kind of again, like a creative, this almost sounds like science fiction kind of question. And then that brings us to the end of our 6th day of this unit. So what I would like you to do next is finish any COSTA questions if you're not already done, and then write your summary for today. There's also an assignment I want you to work on. It's called Solar Science, just kind of reviews the biggest, most important ideas from these video notes to kind of make, because there's a lot today. So I want to make sure it makes sense before we move on. And then I will see you at our next Zoom. Thanks so much for listening. Bye.